This node acts as a central turnstile for AI traffic. Applications connect here, routing requests outward to external large language model providers. To simplify management, organizations are moving away from scattering API keys across individual microservices. Instead, they centralize every credential within a single proxy to handle billing and rate limits in one place. A single database vault aggregates OpenAI, Anthropic, and AWS Bedrock credentials. By consolidating these keys, the gateway becomes the primary surface for attackers. Compromising this single node provides immediate access to every connected downstream model provider. A breach of this central database is functionally equivalent to a full multi-cloud account compromise. CVE 2026-42208 is a critical pre-authentication SQL injection vulnerability discovered in the open-source LiteLLM project. The vulnerability was indexed in the global GitHub advisory database on April 24th, signaling defenders to begin patching. The first active exploitation attempts were logged 36 hours and 7 minutes after that public disclosure. This traffic was not a broad automated scan. It was a targeted attempt to extract the specific tables where the proxy stores its most sensitive provider keys. In this instance, the transition from a public advisory to a manual, schema-aware attack took less than 2 days, leaving a very narrow window for manual remediation. This diagram shows the life cycle of an authentication request hitting the LiteLLM proxy. Every request includes an authorization bearer header. The proxy takes this string and passes it to the backend to verify the user's identity and check their spending limits. The backend handles this by running a PostgreSQL select statement against the LiteLLM verification token table, searching for a row where the token matches the user's input. The application concatenates the bearer token directly into the query. Because it lacks parameterization, the database treats the user-provided string as part of the command's logical structure. This database lookup is the only mechanism deciding if the user can access the system. There are no rate limiters or IP allow lists positioned before this check. The database query executes the moment a packet reaches the proxy port. Because the vulnerability exists within the authentication check itself, any HTTP client can trigger the injection with no prior privileges. This is the payload string researchers observed in the wild. It starts with an SQLi prefix. This allows the payload to mimic the format of a legitimate virtual key during initial processing. The single quote is the breakout character. It escapes the SQL string literal in the backend code, allowing the attacker to end the intended query and start their own. The double dash at the end acts as a comment. It tells the database to ignore the rest of the original application code, preventing a syntax error that would stop the attack. This setup allows the injected union select command to be interpreted by the database as a new, legitimate instruction. The database then executes that command using the high-level system privileges assigned to the LiteLLM service. A single unescaped character converts a routine credential check into a command that grants the user full control over the database. Sysdig researchers tracked this activity to a specific set of requests originating from a German egress IP. The traffic pattern was highly methodical, lacking the noise and randomization typical of automated tools. This diagram shows the logic of a column count discovery sweep. In a union-based injection, the columns in the attacker's query must match the number of columns in the original query. The operator discovered the shape of the database by sequentially adding null placeholders to the payload, moving from 1 column to 6 until the structure aligned. They used the server's responses to confirm the count. Mismatched columns trigger an error, while a perfect match allows the server to return the requested data. Note the shift in table names. The attacker first tried the standard lowercase identifier, then switched to the exact Pascal case format used by the Prisma ORM. The use of this specific quoted formatting matches the internal structure of the LiteLLM source code. It suggests the operator was working directly with the project's schema definitions to refine their attack. This was a manual extraction attempt specifically targeting the 3 tables where the proxy's highest value secrets are stored. To prevent this, developers must stop using string interpolation for database queries. The industry standard fix is the use of parameterized queries. Parameterization separates the SQL command logic from the user-provided data. They are sent to the database driver through two different pipelines. This forces the database to treat the input strictly as a data value. Even if it contains SQL commands, those commands are trapped inside a data container where they cannot be executed. This containment ensures that a single quote can no longer break out of the string and alter the query's logic. For defense in depth, teams should also implement strict in-code validation at the edge. This involves configuring the server to identify and reject headers containing keywords like union or select before the request ever reaches the backend database. Security depends on ensuring that raw user input is never allowed to influence the execution path of a database query. The attack specifically targeted the LiteLLM credentials and LiteLLM config tables, looking for stored provider keys and environment variables. OpenAI organization keys extracted from these tables often have massive monthly spending limits, posing a significant financial risk to the owner. Extracted AWS Bedrock IAM credentials provide a path for attackers to move laterally into the organization's broader cloud infrastructure. Furthermore, an exfiltrated master key can be used to authenticate requests to the proxy from any IP address in the world. Because AI gateways centralize high-value credentials, a successful SQL injection here has the same impact as a major infrastructure breach. Organizations using LiteLLM must update to version 1.83.7 or later immediately to close the vulnerability. If a vulnerable instance was exposed to the internet, administrators must assume the database was accessed and rotate every key stored within it. From a network perspective, AI gateways should never be exposed. They must sit behind a reverse proxy, requiring mutual authentication. A web application firewall can scan for SQL patterns in the authorization header, dropping the connection before the payload reaches the application. Defenders should also audit their model provider billing logs for any API calls originating from unfamiliar IP addresses. Internally, organizations should deploy runtime monitoring to alert on any unusual request shapes hitting the authentication path. AI gateways require perimeter-grade filtering and parameterized data handling to remain resilient against targeted exploitation.